Okay, standing waves on strings now. Okay, so we've done the practical already where we've observed these standing waves. We've clamped a string between two clamps. In our particular case, we had the clamp in a sense at one end was the oscillator, and the clamp at the other end was where the string passed over the pulley. So we've got the thing fixed at both ends. This talks about plucking it. In our particular case, we had the oscillator putting the energy into the string. The one condition for these oscillations is that there must be a node at each end. Okay, so basically if you've got your string, fixed point like a guitar string or a violin string or anything like that, you've got a node there, a node there. You know, if anyone plays a guitar, when you move your fingers up the fret, what you're doing is effectively moving the position of that fixed point and changing the length of the string. And changing the length of the string, you change the wavelength of the standing wave that's produced, and correspondingly, you then change the frequency or the pitch of the sound that's being produced there. All right, so when the string is plucked at its center, the string oscillates at its lowest frequency. All right, so what I've drawn down here, this diagram indicates the lowest frequency, what's known as the fundamental frequency. It's also called the first harmonic. So again, in terms of your notes, I would suggest that this statement here be put into your books, okay? All right, so here's a diagram that illustrates these things. So here's at the top, that's our fundamental. It's effectively like half of a sine curve or half of a wave. So the length L here is equal to lambda over 2 in that particular case, from which we get that the wavelength must be 2L. The frequency associated with that wavelength we've just called F. So the first, well, notice here it says second harmonic as opposed to first harmonic. That's right. The first harmonic is the fundamental. The second harmonic is the next one up from that. Okay, it's a little bit confusing because it sometimes is called the first overtone, second harmonic. But I wouldn't be too worried about the term overtone. I'd more talk in terms of harmonics. So for this second one, it's now like a complete sine curve. So one point in time, the thing is shaped like that. At a later point in time, half a cycle later, it would be shaped like that. And after a full cycle, it goes back to the original position again. So in this time, the length of the string matches lambda. So wavelength is equal to the length, the frequency produced 2 times the fundamental. The next possible mode of oscillation, this one here. So at one point in time, it looks like that. After a quarter of a cycle, it'll be down to there. After half a cycle, it'll be up to there. After 3/4 of a cycle, it'll be back to the middle again. And then after a complete cycle, back to the original position. That's the sequence it's going through. This time, we've got 1.5 or 3/2 wavelengths present there, from which if you just rearrange that, you'll get that the wavelength is equal to 2L/3, and we get 3 times the fundamental frequency, and so the sequence continues, and you could just keep going on, putting more and more of these sections of sine curve in, or half sine curve I've drawn there. Right, what else should we note on this? Probably it's not a bad idea just to note down our nodes and our antinodes then. So we have a node there, we have a node there, we have an antinode in the middle. Let's try a different color, see if it's any more clear. Node, 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 antinode, antinode. No, that's still not too good. Let's go for red this time. So we're going to have node, 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 antinode, 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 etc. All right, so here's an example. A stretched string of length 66 centimeters, plucked at its center. The stationary wave on the string is seen to have one antinode only, and it oscillates at a frequency of 560 Hertz. Calculate the speed of the wave on the string and determine the frequency of oscillation of the stationary wave. All right, so on the next slide, we'll just set the problem up a little bit more. There's our string. We've got one antinode in the middle. Now, this diagram is somewhat exaggerated, but it just makes it easier to draw what's happening. So antinode in the middle. The length of the string, 66 centimeters. All right, so what we need to do is we need to figure out lambda. All right, so I'll leave you to figure out lambda, the wavelength associated with that particular, what we call mode of oscillation. And once you've figured out the wavelength, V equals F lambda should allow you to calculate the speed of the waves in the string. And then you're asked to determine the frequency when there are three antinodes. Okay, so in part B, same length string, three antinodes. Let's think about that. 1, 2, 3, that'll be right. Antinode, antinode, antinode. Now, once you've determined the speed of the wave in the string, that's not going to change unless you change the properties of the string in some way. So the speed is fixed, and what you're now looking at is effectively that you've changed the wavelength down here. And so if you've changed the wavelength, you are going to have changed the frequency that is produced. And here's just a bit of a lots and lots of things with standing waves, really. Nothing particular you have to do it, except maybe stare at it. You know, there's the basic sort of experimental setup that we used. Here's just another sort of diagram over here showing you standing waves. This thing down here, we've got this piece of apparatus. I'll grab that out in the next lesson or two and just show you that, and we can see standing waves there. We'll also set standing waves up in the string in the classroom, I think, so that we can see them with a strobe lamp and look at them in the dark and sort of observe the sort of the changes happening, and the rest of the diagrams really are nothing else to look at there. Okay, determination of wavelength of microwaves. All right, this relates to standing waves no longer in a string, but it's going to be using microwaves, which are electromagnetic waves. They're transverse waves, so we should get a transverse standing wave setup, and we'll do this little experiment in class as well. So what we've got is we've got the microwave transmitter. Nothing to write down here, okay, in terms of your notes though. Microwave transmitter. This receiver. Now that was this thing called a diode probe that I showed you a little bit earlier, which picks up the microwaves. And what we're going to do is we're going to have a metal plate. And the metal plate, so when the microwaves come out and they hit the metal plate, they will be reflected off the metal plate. And then we end up with microwaves going one way, reflected microwaves coming back. We're going to get effectively a standing wave set up. And what we'll be able to observe is a series of nodes and antinodes as we move the diode probe along between the transmitter and this reflecting plate. There's one or two other interesting little things to pick up as we do that experiment, and it's referred to also in the assignment where there's a question related to this when you get to it. All right, and here's an example to do with microwaves then. I suggest that you copy this example out, but if you can do it, do it. It's really not that different probably to the idea of the strings, but if you're having any difficulties with it, we can talk it through in class, okay?